Uh, yes, please. Okay. We were dealing with the RTOS as such, and PSOS was one, or PSOS, or however you pronounce it, one such of RTOS. So, what is important, and there may be many other RTOSs, or the commercial RTOSs, which should be looking after as such. Basically, what you have to look after whenever you are looking for a artist. So, most think from the project management or the project manager perspective as such. Basically, what is happening is for what applications you require artist, how much critical is your timings, so that you decide upon the preemptive, non-preemptive scheduling. How much memory is that particular board or platform is having. So, what is the foot size of your OS by itself? So, minimum footprint or foot size of that particular OS helps you to develop, or the larger space for application development as such. So, footprint. Then priority levels. So, yeah, how what is the support that is provided by the RTOs for the priorities, and how do you make sure that your tasks will achieve their respective deadlines whenever you start creating them. So, how much of file support or memory support is required? Is it available? It is not available. The number of priority levels. So, all these aspects, and even including the libraries. So, most often, when you are searching for the Python or the development libraries, basically somebody else is developing the libraries, or there's a large community support for that particular aspect as such. Editor support, so that how it is developing, so whether you want to have a native compiler, so in-house or in-system development can happen. Then you may go for a normal approach, is a cross compiler, so target and host machine. So even in a PSOS, that is what happening with respect to different tool chains. So whenever he is mentioning xarray plus or PNA, PHP, so these are different tools. So PSOS, that may be particular aspects as such. Otherwise, whenever I want to develop something, I want to have that IDE kind of stuff. So integrated development environment, or the integrated simulation or synthesis. So you require basically an environment which has all the scope for development. So it has an editor, it has a tool chain required for compilation, linking, loading, and downloading onto that particular kit, and then going for simulation as well as emulation. And then once you have developed, so you can make that particular system standalone after once you download the entire code onto the, or there are two versions of code: debug mode and release mode. So ultimately, whichever is the commercial version, so in removing all the debug information, the code can be very compact, and hence that can be downloaded. So these were the aspects with which an RTOS should be evaluated whenever you are studying commercial RTOS. Otherwise, they are just data sheets. So there is nothing me to explain as such. So I just go on explaining PSOS as so many interrupt levels, or the code size is 20 kilobytes or 40 kilobytes. Some number is depicted with which you are evaluating a system as such. Right? So preemption point, this already we have discussed, but again for your information, I just want to go ahead and say where you can preempt or make the currently executing task to preempt a particular CPU. So that is what is studied. So entry or arrival of a task, or arrival of a task with a higher priority number. So these are the preemptive or preemption points as such. Fully preemptible kernel, whenever something is running in kernel mode, normally the other things, interrupts and other tasks are will be disabled, because the kernel will be having the highest priority. So you require some resource locking, or the you want to have that. So user task request some system calls, and that it goes to the kernel priority level, and it has to lock the resources. Then there were two kinds of locks that were proposed. So kernel level locks. So the invariably other task which is having a lower priority than the kernel priority has to wait until the lower priority task, because it has acquired that kernel level lock. It accomplishes the task unless until it accomplishes, the higher priority tasks has to be made wait. But normally what happens, the spin level lock or the spin locks are designed with respect to the aspects as such. The shifting or the context switching time by themselves are almost very small. So you go back, and by the time you are going back by cleaning up the stuff whatever you have done, so the space required for you is readily available. In that sense, spin locks were made an alternative for the kernel locks. So what happens is, if T2 is requesting a kernel lock, so it doesn't vacate from the ready state, so it doesn't suspend itself, so it goes for a wait state until the resist becomes equal. So maybe 1 millisecond, that is what is the waste clock takes. So in the next clock cycle, the resource required by it is readily available. That is what is meant by spin locks. So we move to the commercial RTOSs. So recapitulation, last few classes we have discussed requirement for RTOS. So what were the basic requirements? We studied them. Then what is meant by POSIX RTs, or the portable Unix RT, or the where you started studying something like a open system, open object, then open source, and finally open binary, which is most of the theoretical stuff. Um, Lastly, a standard, so that it advocates that open system concepts into POSIX or the POSIX RT 4, which is real-time extensions, that was addressed. Difficulties using Unix and Windows for RT applications is the initial phase of the chapter. So that because of that OS or there was a tabular column which was comparing the OS or the deferred procedure calls in case of Windows. So then the number of priority levels, or the dynamic priority levels, or the non-preemptible kernels. These were the issues that were discussed, or what is limiting the Unix or Windows systems to be an real-time operating system were discussed. So the specific aspects of designs of these OS that create difficulties, yes, they were addressed or discussed as such. If you can recollect them, that is very well and good. Two main approaches, so which normally stopped, is preemption improvement. So how fast you can preempt, or how fast you can accomplish that task. So otherwise, normally no, Unix and Windows were non-preemptible kernel. Interrupt abstractions. So interrupt abstractions, we stated something where some interrupt normally will go into DPCs, or deferred procedural calls. Whatever is really critical in that particular interrupt will run immediately. So otherwise, if the interrupt by itself is having a lower priority, it is run as any other task in the task queue. So it is put into the task queue, so ready queue. So whenever the turn with respect to its priority number comes, so it is made, the processor is made available to it. I think somebody was pinging. Okay, Bandri. Okay. Preemption improvement. Linux kernel code is modified. Amount of the time that kernel spends in non-preemptible part is reduced. So normally Linux is the residential kernel or the non-preemptive kernel, but that part is reduced, so that most of the kernel space can be utilized by the application space. You can just make it simple for that. Main strategy adopted: reduce length of longest section of non-preemptible code. So what is really delaying you, make it run as a task with a lower priority, so that there is again a partitioning, or the a particular piece of code or a task into many subtasks, so that the priorities can be assigned appropriately. So this would minimize the worst case latency of interrupts in the systems. So you choose whenever a task, or it may be a hardware interrupt, that is normally called as a ISR, interrupt service routine, or it may be the software interrupt, or the called as a DPCs, or deferred procedure calls, or DSR, deferred service routines. So that's where you are deferring them by a particular amount of time, so that what is critical and what is non-critical is at the discretion of the programmers or designers aspect. So you should visualize that aspect and make it appropriate. Interrupt abstraction: instead of instrumenting Linux kernel to increase preemptibility, the entire kernel is made preemptible. So the major obstruction was non-preemptible kernel. Now you are attempting to make it preemptible. As a separate layer, intercepts and manages the hardware interrupts. So somewhere an approach to manipulate, or the do some modification with the HL, or hardware abstraction layer, is done. So hardware abstraction layer has complete control over the hardware interrupts. Under the real-time scheduler, Linux kernel runs as a low priority task. So basically what is running is a plugin kind of stuff, what has to be in a real time. So maybe if you can recollect, 0 to 128 were the priorities reserved for the real time kind of task in the Unix environment, or there was some static priorities were there even though the priorities were changed dynamically with respect to the utilization factor of that particular task as such. So some plugin was introduced, or the RT Linux patch was introduced, so that really you are learning, but whatever has to run with respect to time criticality will run as a RT Linux or the real-time Linux patch as such. This approach increases preemptibility in the Linux kernels, so that kernel can, by itself can be preempted, guarantees the longest measured interrupt latency. Um, so ultimately, you want to reduce that latency and make sure that all the tasks are able to meet their deadlines. Does not provide guarantee about the maximum latency, so difficult to examine every possible code path in the kernel. So ultimately, it's a patch, or the background worker is a leisure worker. So Linux kernel is what you are manipulating, so the particular part of that can be made as a real-time aspect as such. So ultimately the owner by himself is somewhat leisure, so there cannot be guaranteed latencies as such, because RT Linux, or the RT real-time aspect of that particular Linux, is again managed by the main Linux kernel. So hard real-time performance guarantees cannot be made. So there is still kind of certain kind of uncertainties, but still at least some kind of predictability can be done for something which has to be very real. So whenever you categorize the systems, so hard, soft, and other stuffs, maybe for soft and firm real times, you may consider these real-time extensions for the Linux kernels as such. So Linux kernels of the interrupt abstraction model, Linux kernels runs unmodified. So basic core or the main kernel is as it is. So kernel loadable models. So there is some aspect of the APIs of the application KPI or API is made as a preemptible. That is kernel loadable models. Sub models are being created. So limitations of interrupt abstract model, real-time applications are becoming more and more complex. So you have to attain the or meet the deadlines, but okay. So real-time applications are becoming more and more complex. That somewhere deals with the market strategy. So normally embedded systems, or whenever you targeted that particular specificity, now that is becoming somewhat diluted over there, and hence it is making the things more and more complex. So whenever you say there should be predictability, then you should go with respect to one aspect, or the if you know that I'm going to do this for my lifetime, you can optimize your entire life, so you can focus, this is what you are going to do or study. uh, what happens is most often we offer as a generic solutions. That's where all the problems begin. So I want a fridge, but I want some LCD display to play video game on my fridge, or cell phone as it has evolved. Everything is my cell phone now. Otherwise, what is intended of cell phone is to locate where you are. Where are you? So most oftenly, home location register or visitor location register, that has to be updated with your base station for every 30 milliseconds or 20 milliseconds, so on. So that is somewhere the real-time aspects of, so that you are being tracked appropriately, and your quality of service promised by that particular vendor, maybe Airtel or Vodafone, whatever your service provider is there. So he has to maintain that service level agreements. So with respect to that, you have to be updated. Otherwise, some call drops will happen. So that is really the real-time aspects of a cell phone. If I'm just considering, even that is not full-fledged real-time operating system. So that aspect is at least real-time. But you start invoking, say, I want to have 40 megapixel camera, some image processing has to happen over there, or some video compression algorithm. So whenever you start including many stuff, so that specificity is lost, and the systems start becoming more complex. Just one example to make you visualize that how things are becoming with respect to market strategies. Otherwise, initially, whenever you had a camera, so camera was only meant to take pictures, or whenever you had a concept of phone is only meant for making calls or the voice oriented communications. So system dilutions or upgradations, whatever happening in the market, will affect the things, and so things has to deal with respect to that aspect. So that is what is added by with the complexity as such. By nature, real-time embedded systems, so they are constrained, so with respect to memory and what should be where. So that deals with the OS, and OS has to manipulate only certain kind of registers. Other kernels should not, or other tasks should not be able to manipulate. Then you require some stuff called as memory protection unit. So there is a virtual memory concept. So you are not going for a direct addressing. So I have 16-bit address lines. So then I can access 65,536 location with respect to 16-bit address bits. But I want my phone to access more. So maybe 4 GB, or as in case of your cell phones, a 32-bit processor is made to access somewhere around 32, okay, beyond 4 GB. So those virtual memory or the indexing of the memories, if you can just simplify that, so that additional VM concepts, so they are complicated or not required for the real-time systems. Maybe a certain limited versions of the file systems or the memory management systems are to be done over there. Process isolations. So how do you make sure that the sharing between the processes and tasks are made intact? How do you lock them and make sure that the clean resources are available for the processes and tasks, or the message passing or IPCs are happening with respect to the system interprocess communication. So RTI is one such plugin. We have mentioned of this already, real-time application interface underlying architecture for the RT Linux. So quite similar for both Linux operating system. It runs as a lower priority task of a real-time kernel. So one plugin that is added for your Linux. Basically, your Linux is, yes, it's not much bothered about the timing. It's more bothered about the functionality. But some aspect of the stuff or kernel, a limited edition of that, limited edition on some limited part of that kernel can be made as a real time. That is what is meant by using a real time application interface. So whenever you are making some system calls provided by RTI, it makes sure that your timing with respect to that accomplishment of a particular task is somewhat predictable. So limits the changes to the standard Linux kernel by adding a hardware abstraction layer, so that however interrupts and other things are manipulated. In contrast, RT Linux applies most changes directly to the kernel sources. So this is application interface, and RT Linux is a modified version of Linux. That's how one is a plugin, another is a separate version which is trying to promise all the real-time aspects of it. RT Linux ಅಂತ ಹೋದಾಗ. So RT kernel intercepts all interrupts. So if interrupt is to cause RT task to run, RT kernel preempts Linux. So even the Linux is made preemptible. That's what is to be inferred from this, and lets the RT task to run. So preemptible kernel aspect is adopted. Different models of the kernel can be selectively loaded. So not all the models simultaneously. Whatever is required or custom tailoring can be done with respect to loading and unloading of the Linuxes. So priority levels both are supported, fixed and dynamic priority levels. So as far as real-time things are considered, most predictable or static is preferred. Sometimes with respect to emergencies or interrupt handling and other stuffs, even dynamic priorities may be preferred as such. So context switching time is reduced. So if you can think if you can recollect that kernel switching times with respect to Unix or Linux were somewhere with respect to milliseconds to seconds. Now the context switch time compared to that is very much less, or almost nullified, 15 microseconds context switching time. The biggest advantage, source code is available. RT Linux, whenever you want to manipulate, custom tailoring, whenever we attempt that terminology as such, open source. So the source code is made visible. So you read the intentions of the kernel development, or the, and you can manipulate as per your requirements as such. So if specific drivers or specific part of the kernel is known to be causing undesirable delay, you can manipulate and get your things done. So fine tuned. So hardware, it speaks to Linux kernel using system libraries or system calls, or the you can go other way. So user processes will access system libraries, and through system calls with respect to any OS you are having Linux kernel or device drivers will speak to devices and get your things done. So what is happening with the RTLS kernel? So device driver, that aspect or the hardware abstraction layer was scheduled over here. So you can accomplish some real-time tasks. So a limited set of tasks which can be real-time. Major set of tasks are still can go into soft kind of soft real-time arena, so executed in the background, and basically this is what is running. Some portion which identifies this task has to be real-time with respect to its priority number, or the real-time Linux plugin whatever is introduced will take over with respect to the, or make sure that the tasks are scheduled first, and they get things well within their deadlines. So, what was the stuff that was happening with Linux? System calls were normally taking long time to change the mode of preemption. This overhead is eliminated by running real-time task process in kernel space by themselves. So, whenever you want to accomplish anything, so who is the owner? OS is the owner, and who is or what is OS right now? It's a Linux OS. Every time you have to ask him, but that entire process or procedure or protocol by itself was taking a much larger time. Say, again, if you can recollect Pentium 4, so get timestamp or the set timestamp whenever you are reading that. Uh, Reading by itself, so what is my current time for reading itself? If I am taking 1 millisecond, and then the what is the validity of that information after 1 millisecond has to be questioned. So running into real-time process kernel space, so that differentiation or gap can be reduced. So ಇಷ್ಟು ಟೈಮಲ್ಲಿ ಆಗಬೇಕು ಅಂತಂದರೆ, ಸೊ that is identified. How do you identify some task is real time or unreal time is basically the priority numbers, and hence once the priority numbers are seen, now it is up to the schedulers. This should be done by me, this should be done by somebody else, or I have appointed a one more person called as a real time Linux manager. He will look after that particular category. If at all he fails, then anyway I am there, it will look after that, whatever the exception that may arise. So basically, Linux is running in the background. So RT Linux comes to the foreground and starts managing their tasks as such. So advantage of executing real-time tasks in kernel space prevents threads from being swapped out. So ultimately, they have got a kernel priority numbers. So no other task can preempt them. So once they are running as a kernel, threads are executed in processor supervisor mode. Supervisor mode is basically you have all the rights, so you can manipulate. So accessibility, you are running as a kernel. So whenever you are in kernel mode, you can have that changing program status word or switching modes. Everything can be possible if you are running this supervisor mode. You can enable, disable interrupts. All that can happen in the supervised mode. If you are running in the application mode, most of only uh, you are running plain applications as such. Uh, Okay, RTOS and the application share single address space. That means how do you manage memories is an aspect that has to be discussed over there. System call becomes simple function call. Software interrupt has a higher overhead. So through system calls, again, RTOS APIs or the application program interface through which you want to manipulate that. Ultimately, the memory is same. So the memory space is shared between whether you are handling a real-time task or you are handling a normal task in Linux. The memory space is shared by both, or there is the same space. Now, what happens whenever you share? So data integrity becomes a question mark, and that has to be protected. And there should be some mechanism by MPU or MMU in it, so that may be really part of Linux or not in Linux. So performance improvement in the RTLinux scheduler treats Linux kernel as the lowest priority real-time task, because our real-time task is another plugin or the kernel is readily available. Linux kernel is lowest priority. Users can use their own schedulers, use as loadable kernel module, so we can have some freedom over the scheduler, how the task can be scheduled, maybe round robin or the first come first serve basis or EDF. So that with respect to that real-time aspect or real-time plugin, you can manipulate that stuff. So timers in Linux, one of the requirement analysis that we addressed whenever RTOS were being done. So there was a timers, so and timer handlers. So whenever that interrupt occurs, whether you are using a periodic timers or the one-shot timers, as in case of first timer, whenever that triggers, there is a something like a service routine or the similar to after that timeout and interrupt generates. So you have to search or do something with respect to that timing. How many timers that OS is providing becomes an important aspect of system design as such. So timing inaccuracies cause deviation from the planned schedule. So whenever you are having the timers, you are deriving your timing from the hardware clocks. So ultimately, whenever a board is designed, there is one crystal oscillator. After that, internal to the processor, there is some machine cycle, clock cycle. So some adjustments, and ultimately, at OS level, you start seeing OS ticks, so system ticks. So there are variations with respect to all these clocks. So ultimately, whenever you are making the other timers, so again through system calls may have their own context switching times or the jitters. So and hence finally there is a deviation with respect to arrival and exit times or something we want to accomplish. So whenever I ask a time, so there is some certain margin which can be accepted well within the system norms as such. If I say my class starts at 9, so 9:05 is okay, 9:10 is okay, 9:20 may not be okay for me to continue the class. So, with respect to that system sensitivity, how much jitter is acceptable? So that system designer will look into and has to decide. This is supported, and now once you have decided and you know what is the system calls of you, how do you decide 9:05 is okay, why 9:10 is not okay? So that is made sure that maybe something is missing or something catastrophic might be happening in that particular system. So you decide with respect to that jitter space, or timer should be accurate as possible, but ultimately inaccuracies will prevail. How much inaccuracy is acceptable, it is a system designer's purview, and he will look into that particular aspect. So standard desktop Linux programs, the hardware timer interrupt at 100 hertz, example at 10 millisecond precision. So what is the precision of Linux programs, where whatever the clocks, whenever you say sleep or delays kind of routines are being used in your C programming or system libraries, ctime.h or the timing.h. So they are able to produce 10 millisecond precision. So whenever you call the delay 1 millisecond, so basically it is able to produce that 1 millisecond delay. Somebody has written a routine and clock, everything is taken into account, and you are able to produce that delay. So that's what is really conveyed over there. RT Linux can use a hardware clock to provide 1 microsecond. So compared to the 10 millisecond with respect to Linux, so Linux 10 millisecond, RT Linux 1 microsecond, considerable approach, and hence so ultimately jitter. So deviation from the arrival and exit with respect to clock can be seen. Programmable interval timers. So again, if something is not possible or not going really accurate with respect to software approach, then invariably somebody has to switch to hardware approach. So 8354 is a programmable timer. So you directly connect your timers and whatever the delays you want to have with a periodic one shot, so that can be accomplished by some hardware clocks. So 8354 is one such timer, most often is studied with respect to 85. So inter-process communication at Linux kernel can be preempted by any real-time task. So he starts discussing with respect to inter-process communications. How do you communicate between processes? Uh, so communicating using standard Linux primitives is not a satisfactory option because there is a delay involved in them. Simple FIFO buffers are used for inter-process communications. So pipes, queues, so then message passing. So some kind of semaphores if you are going for a locking of systems. That's what are normally has to be studied with respect to inter-process communications. So most often the simple pipes or the FIFOs or buffers are used for inter-process communication. Shortcomings of RT Linux. Duplicate coding. If a task cannot make full use of existing Linux system services, because development and the ideology with which the Linux or Unix was developed, and the development with respect to real-time scenarios of the RT Linux are quite different. So whenever you are purchasing a PC for a kind of application, same laptop, so maybe you start seeing into the RAM, ROM, or the whether there's a graphic card. Sometimes I want to do cadence, sometimes I want to play a game, sometimes I want to play a video. So there are diverse applications with respect to the operating systems, general purpose operating systems. So whenever you choose a set-top box, even the channel changing blanks timings, yeah, I switch from 700 to 701. So whenever I'm making that channel changing time, so that irritates a user. If you think from that perspective, so it should happen almost instantaneously. Then how do you make sure that there is a least blank space with respect to the OS running in my set-top box or whatever it is? So that is what should be seen with respect to operating systems. In the Linux only, timing, yes, it accomplishment of a task is still there, but file system networking, more demands are there, or diverse demands are there rather than more demands. So fragile execution environment, processes run in unprotected kernel space. So again, thinking back from the DOS perspective, you may, if you are running everything in the user space, even the kernel files may be deleted, and next time whenever you want to boot or you crash somewhere, so your system is not booting. That things are to be completely avoided. So what has to be run in the application or the user mode has to run in the application mode. Something you are doing very critical, then go to the supervised mode by intentional SWI or SVC instructions, software interrupt or the any so that there is a mode shifting, and something you want to manipulate intentionally with respect to that particular program as such. uh, Small subset of APIs or POSIX APIs. So you are not writing entire stuff. So some limited set of Linux is taken. So POSIX API. So whatever is supported with respect to API is application program interface. So something similar to system calls. So moving existing Linux code to RTOS becomes very difficult. So there is some limitation for that, but still, uh, it is as good as reading. Something is better than nothing. So there is some limited version of Linux which can be made as a real-time Linux kernel, and most of all, what is more advantageous, it is free for that matter. What is disadvantageous? Support if there is a more activity with respect to your project or the kind of project you are doing with respect to Git, whatever GitHub or Adafruit, whatever the development you are doing. So you may have immediate answers for your project solutions for that. So if you are stuck up with a strange kind of error and nobody is working on it, so maybe you are in a soup. Coming to the next OS, again, Micrishim was a company which created by this micro MUSI OS 2. So there are different versions now. Current maybe three, earlier whenever I taught the RTOS, it was Micrishim 3 was available. Now it will be 4. I don't remember as such. So what it basically states is a microcontroller operating system version 2. So footprint is about 20 KB, so with which you are evaluating any operating system. Then the source code is about 5,500 lines, and most often written in C. Its source code is open, but not free for commercial users. What it means to you is basically, as an academician or as a researcher, you can use it. So Magnesium OS or the APS, you can develop an application and enjoys the results and publish your results. You are done. So something usefully or donate for the society. But if you want to make a product out of it and then you want to sell to the market, then you are missing, or you are not providing the share by the Microsim OS, because you have used their contents, and legally you have to provide the profit share to them. So that's where the commercial aspect comes into picture. So for development and the research purpose, so they're not charging. If you are developing some product and you are earning from it, so then definitely you have to provide some royalty for the OS you are using. So that is what is microchips basically. Footprint, interrupts, preemption. So whenever you are reading, so in with respect to a textbook or with respect to slides, so with you have to have that in your background or in the back of your mind, so that you are evaluating that system for that particular aspect. So, OS2 has been designed as a small footprint real-time preemptive operating system designed for embedded use in 8-bit platforms and ports. So, it support for 8051 as well. Coming to the ARM and other architectures, preemptive real-time multitasking kernel is there. Over 100 microprocessors are supported. How many microprocessors? It is again basically speaks about portability. If you are designing something with respect to migration OS or the system calls, so most often they are supported by somewhere 100 and odd microprocessors. That is, it can be seen with respect to that. So scheduling aspect round robin scheduling is not supported. So memory he is not stating which is supported. Maybe the first come first serve is supported if it is not round robin. Memory management is performed using fixed size partitions. Again, normally they are called as memory pools or buffers. So rather than the full-fledged VM or virtual memory concept is not supported. That's what is meant by that. One OS or one commercial is OS is what next ECOS or embedded configurable OS. One more OS, and open source. It is a royalty-free RTOS, so you need not pay anything for anybody. Just use it and develop. And he is also not restricting anything for your earning as well. Whenever you use it, if it satisfies your needs and you develop a product, you can just freely market it and get whatever the earning you can make it out of it. Integrated for embedded applications, highly configurable, allows OS to be customized to application requirements. So OS to be customized to application requirements, that means it's open source, so you can view the code and you can manipulate or custom tailor as per your requirements. So the site is showcased, or you can go to that particular link and download, and if you want to develop something with respect to that, you can go ahead, definitely. But whenever that happens, ultimately you require some platform, some debug platform, which is not, say if I want to have a ECOS onto my Keel compiler, there should be third party support, what I am expecting from Keel compiler or any other compiler for using such kind of OS and system calls. So high volume of applications, consumer electronics, telecommunication, automotive, this is where it is being used. Real-time tasks run in kernel mode, no user mode. So earlier case it was a C in Microcium OS or MicroMusi OS 2. Now implemented using C++, because it's implemented using C++. What are the features? It gives a choice for scheduling algorithms, so you can switch between the algorithms. Choice for memory allocation strategies. How do you allocate, whether continuous, non-continuous, fragmented, unfragmented, and so on. Timers and counters are provided. Support for interrupts and DSR, deferred service routines, or procedure calls, which was the case with respect to Windows. Exception handling. So good exception handling support, so that still you maintain the timing. Host debug communication support. So debug communication support is basically you have to plug in through some USB or Ethernet cable. So host target approach or development approach. So you can generate vectors and dump it onto the OS. So output vectors are collected and compare with respect to valid responses. So then you can validate or verify whether things are working as per your requirements or not. Okay. Yes, we have discussed this. No problem. So one more stuff for VRTX, versatile real-time executive was developed by Ready Systems in 1980s, but acquired by Mentor Graphics in 95. It is suitable for SoC kind of architectures, or what is meant by SoC? Anybody? System on chip architecture. So basically, you are synthesizing your processor, you are synthesizing your ROM, RAM, entire stuff onto the same chip or same FPGA, and you are compiling your code onto the, with respect to some platform, say OS, and you are developing application, and that application is dumped into a particular ROM or RAM into that FPGA. So entire stuff. So those kind of supports are provided by the VRTX or versatile real-time executive operating system, or RTOS. So traditional board-based embedded systems. So most of the embedded systems are board-based, or the daughter card-based embedded systems as such. So I can compare the 20 KB or the, now it is 4 KB size, did not support many required functionalities. So whenever you see that reduction has happened, or there's a trade-off with respect to the functionalities as such, could not be used for full RTOS. So there is some limited versions. So what comes, the versions he has divided with respect to VRTX SA and VRTX EMC. So MC stands for the microcontroller, optimized for low power consumption, ROM and RAM sizes. For limited or constrained environment, whenever you are going for embedded application or microcontroller based applications, normally the resources are limited. But what is important is it is authenticated or certified by Aviation Authority (FAA). So that gives some glimpse that most oftenly VRTX was meant for aviation industry because somebody from aviation industry certifying this OS, maybe their braking systems and other stuffs were dealt by VRTX. So for safety critical applications such as avionics, VRTX was preferred. So targeted for products where memory efficiency and the low power consumptions are important. So most oftenly the embed application or portable application or portable products, so battery operated products. So where it is used or it was used, so set-top box, digital cameras, video game system, rotors, handheld computing devices. So to be famous or the most of the applications were with respect to the Motorola cell phones, VRTX MC, initial Motorola's. Again, I'm restricting. Now, most oftenly, your cell phones are loaded with Android, maybe 10, 11, whatever the versions may be. Again, we'll discuss that aspect. Maybe there will be one question with respect to that for your assignments. So functionality superset of where TXMC. So where something you cut down for the limited edition, maybe file systems or memory management systems, which were not taken into account for the microcontroller systems or the small embedded systems. Now you are adding them. So it is a superset. So SA stands for that superset. Um, it is POSIX RT compliant, so it follows that open system architecture, whatever is proposed by POSIX RT extensions, designed for medium and large applications. So footprint size can be decided about with respect to that. So extensive I/O support. So most of the device drivers, the I/O support is made available whenever you start using VRTX ESA. Reduced interrupt and task switch latency. Okay, context switching is reduced or the interrupt latency is reduced. So other features support priority inheritance and multiprocessing. So you studied them PIP protocol, which was again with respect to an example of VXWorks. Maybe next slide is speaking about that. It used a similar kind of inheritance protocol and multiprocessing. So most of the things. So whatever the commercial autos we have discussed. So there's a SMP concept or symmetric multiprocessing or asymmetric or heterogeneous multiprocessor. Whenever you say multiprocessor environment, so processors can be same or processors can be different, and that leads to further complications about things with respect to processors. And even if you want to complicate much more, so there are multi-processor, multi-operating system are available. So within a same system, there are different OSs as well different processors that are being used. So we'll not jump to that aspect because at the course is at introductory level. So what we will restrict ourselves is basically it supports some of the priority, so resource sharing or the priority inheritance protocol, so that unbounded priority inversion kind of stuff is reduced. So it also supports multiprocessing, so even though there is no mention about whether it is SMP or asymmetric multiprocessing. So same processors or different processors that are being supported within a system as such. System calls are fully preemptible and deterministic, so there is more predictability and hence it can serve as a operating system. So examples, so it is used in as a Hubble telescope. So VXWorks, again PSOS, whenever you study, say maybe you have heard the name of WinRiver system. Now VXWorks also is manufactured by WinRiver system. So Intel acquired WinRiver system in July 17, 2009. Is based on VRTX, so which is a it has most of the things copied from VRTX. Many features of VX are similar to VRTX, and most of your PLCs, industrial automation, are running onto the VXWorks operating system. Several features and development environment. So most often it has some environment name called as a Tornado, which gives some IDE kind of approach where you can develop an application, download, simulate, emulate with respect to particular board design as such. So it has a symmetric processing or symmetric processor support. So multitasking kernel, preemptive and round robin scheduling, that is what is adopted in the VXWorks. Memory protection, application isolates from the kernel. So ultimately there is a MPU unit or which isolates kernel space and the user space. Semaphores with priority inheritance, binary and counting semaphores are being implemented, even though they are costlier affair for the RTOS as such, but still they are there. A shell-based user interface so that you can communicate in the runtime. So most often cd, make directory, delete, ls, whatever the commands we are issuing are based on the cells as such. Some user aspect is been provided so that user can interact to the OS with respect to shells. File system is also provided. Yes, it's a costly affair whenever you think from the real-time operating system. VX simulator, yes, that's appreciable aspect of the RTOS of the any operating system or the any developer will be happy with respect to that environment or KDE, kernel development environment or the ID integrated development environment. So that all the toolchains required for me. So how do I give my ideas of the design entry? So maybe the editor, so it automatically highlights my keywords. Int is in blue color, variable name is in black color, so some kind of support for that. That is editor support. So then later part linker, loader, compilation. So including that sim simulator, basically some debug information with respect to traces, watch points and other stuffs are readily available. So as I stated, there is a ID called as a tornado with which you can accomplish that particular stuff. Symbolic and source level debugging capabilities are made available, so that we discussed as an integrated aspect as such. Performance monitoring, so most often called as a coverage aspect. So you can see that what is covered and how many times a particular code is triggered or the piece of code is triggered, and then something should be optimized or this is really hampering you. That can be detected from the code coverage, so that can be manipulated as and when required. What is one more strange thing is monolithic kernel. So normally the RTOS, as we discussed in the initial slides, most of the things were to be developed in the user mode whenever really required, or the microkernel approach. It's not there. It's a monolithic kernel, RTOS compliant. In addition to its own APS, host target. So it has its own APS. That means some application program interfaces are only for the VX works. So whenever you are using VX works, you can use them. Apart from that, there are generic open system interconnect which were recommended by POSIX RT Linux standards or the RT POSIX 4. So they are also supported. Host target approach, that is a development cycle. So what we stated tornado, and how do you connect maybe through USB to that port is connected and you want to download it and get the output from the board and plot it on the graphs and see something is happening over there. So all that supports required for that. So the binary license at the board level as well as the host target level, so they are made available. So some support for virtual memory is provided, that is provides virtual memory to physical memory mappings. Um, Application development on a Unix or Windows host machine, so that you can install Tornado onto your Windows system or Linux machines, develop an application, and then download it onto the target port. Cross compiler helps for running applications. So basically, what is happening is host machine. Whenever I state, maybe it is Intel i5, but most of the applications you are running onto the are maybe 8051 or ARM LPC 2148 or 1768. There will be or large class of your cell phones, maybe OMAP, a TI OMAP processor. That's where the things are be supported. So various target architectures. Most of in the previous slide or the previous OS, he was mentioning the numbers, maybe 100 microcontrollers. So you can just count. There are more number of architectures that is supported by Xbox. So runs on host through VXM. So that's how it is implemented. Tornado we have already spoken of. Anything new? So all these are called as a tool chains or the cross compiler, debugger, host target communications. So watch points and also whatever required supports are there. So that's a ID or integrated development environments. This case study is also addressed in the slide whenever we are discussing about unbounded priority inversions and one of the protocol called as a priority inheritance protocols. So deep impact. So something in the space was to be fixed up, and there was a kernel reset or the every time the that particular Mars Pathfinder was being reset several times. Uh, then people notice that whenever they are compiling kernel, one option called as enabling that PIP protocol was missing, so it was disabled, and hence the tasks were not able to complete, and that hence they forced it to for many or multiple resets. The same scenario was recreated because of the debug environment or VXIM, whatever the boasted stuff torrent ID we stated previously. So they simulated it and found out that this was a bug, and they rectified, recompiled, and uploaded it onto the satellite source. They ported a newer version of code onto the stuff, and the things started working correctly. Fine. So other things where it is being used, so Boeing Airlines or the wireless router and medical solutions of the ABB robot and so on. Links basically most often the automotive sector is working with the links. It was released in 88, fully preemptible, re-entrant and compact. Monolithic architecture to microkernel design. Kernel size is 28 KB, provides essential services. So this interrupt dispatch or synchronizations, whatever can be straight. So it states instead of using the terminology of API, he started using something like a KPR, kernel plugins, KPS, are multi-threaded. So there is a hyper-threading or creating multiple threads so that context switching time is reduced. So with that intention, they have created it. So the I/O handling is made more realistic or real-time. File system is supported. So TCP/IP protocol or the internet protocol is supported. So streams and sockets so that can or internet or the socket programming is supported with respect to the communication aspect. Again, definition of microkernel takes as much of the kernel as possible, out of kernel as possible. Minimalist approach. So you create one microkernel, a modular small, 10 kilobytes or even few hundred kilobytes. So that he is speaking with respect to the kernel size as such. Easier to port, maintain, and extend. And whenever you want to develop further stuff, so most often the things will go into the user space and make it happen through the system called so the kernel. So monolithic kernel, single kernel, almost equal space for kernel mode and user mode. So kernel is tiny, and most of the applications developed will also have that. These were earlier in the kernel itself. Now they are developed in the application space as such. So links can function as multi-purpose Unix OS. What he really means by that, I don't know, but basically links is basically used in the RTOS or the automotive sectors. That's for OS is used for basically as a resource management. Multi-purpose ಅಂತಂದ್ರೆ ಏನು ಹೇಳ್ತಾರೆ ಗೊತ್ತಿಲ್ಲ. That may be again, if I look into the examples of the previous slides, he may be stating about that router, air Boeing or satellite or the Mars Pathfinder and so on. So that may be the things. So with respect to the application, you have to again custom tailor and get your things done. Other services provided as a kernel plugins, KPS. Kernel is protected, so no other thing can damage it, so because user space and kernel space is separated. Memory intensive applications, example compilers, debuggers, etc. access memory through MMUs or the memory management unit is made available as a component in the links OS. So suppose a single scheduling policy, fixed priority preemptive with 256 priority levels. So if you can refer to your previous OS versions, maybe VRTX, PSOS, VXWorks. So just compare with respect to number of priority levels, and whenever you are developing an application, then you really come to know that whether how many priority levels are really sufficient or insufficient. Other than that, you just are happy with the numbers 128, 256, yes, larger, better kind of stuff. Clock tick frequency is fixed out 100 Hz. So resolution time of timers is 10 milliseconds. One more stuff for QNX is QNX Newton is one more OS. Unix like, or most often if you can say broadly, they are copied and polymorphed versions of the Unix systems as such. So developed by Gordon Bell, Dan Dodge, students of CS. Again, what makes me happy is contribution from the universities. So it's from the academic section. It is not Bell Laboratories or AT&T Laboratories, kind of stuff. So microkernel design, kernel provides thread and time services, allows developers to easily turn off any functionality they do not require. So the customization is allowed. That means it's open source, and that is what is stated. Every driver application, protocols, and file systems customization runs outside the kernel. Applicant portability. So portability speaks about how many processors or the architecture it is supporting. Any component can fail and restart it. That means without affecting the other components. So that means some kind of watchdog environment is made available within OS. I don't know how they have implemented it, but yes, that is available. Almost every service runs as a user process. So you are running in the user application as a normal case, includes a special process known as a proc, which performs process creation. So one API or KPI is stated over here with respect to the neutrino. With the help of microkernel, due to the microkernel architecture, QNX is also distributed, a distributed OS. So distributed means fast kind of approach. So from next class onwards, we'll start looking into Windows CE. This I think maybe the last commercial OS we'll be addressing. Maybe Android, yes, Android on the Paco. Then we jump to the next chapter as such. So any doubts, please post it on the classroom. So currently we'll stop at